In the 1960s, NASA came close to launching a nuclear-powered rocket into space. That project was shelved, but now, over half a century later, nuclear propulsion is back on the table with a $300 million investment. What changed, and why is NASA betting big on this technology now? The story begins during the height of the space race. President John F. Kennedy's ambitious vision for space exploration went beyond the moon landing. His administration recognized the potential of nuclear propulsion to revolutionize space travel, leading to the creation of groundbreaking projects that would shape the future of space exploration. In 1961, NASA and the Atomic Energy Commission joined forces to launch the Nuclear Engine for Rocket Vehicle Application, or the NERVA program. But this initiative wasn't starting from scratch. It was built upon Project Rover, which had been exploring nuclear propulsion concepts since 1955. The NERVA program was a major breakthrough in nuclear rocket technology, with engines that are significantly better than chemical ones. The NERVA program quickly gained momentum, achieving a series of impressive milestones. Engineers designed a variety of reactors and rocket engines, each more powerful and efficient than the last. The program's best achievement was the NRX engine, which produced an impressive 334 kilonewtons of thrust, meeting the requirements set by the Marshall Space Flight Center for its Mars mission plans. As the 1960s progressed, the potential of nuclear propulsion captured the imagination of key figures in the space program. Wernher von Braun, the director of NASA's Marshall Space Flight Center and a central figure in the Apollo program, became a vocal advocate for nuclear-powered Mars missions. He proposed an ambitious plan to send a crew to the Red Planet in November 1981, with a landing scheduled for August 1982. This timeline, unthinkable with conventional propulsion, showed just how transformative the NERVA technology could be. The program also produced the Phoebus 2A reactor. This behemoth ran for over 12 minutes at a staggering 4,000 megawatts, earning the title of the most powerful nuclear reactor ever built at that time. Yet, despite these promising results, the NERVA program met an unexpected end. In 1973, after years of successful development and testing, the program was canceled. Why? The early 1970s saw a shift in national priorities, with the Vietnam War and domestic issues taking precedence over space exploration. President Nixon's administration, facing budget constraints and changing political conditions, made the difficult decision to terminate the NERVA program. NASA was also pivoting towards the development of the Space Shuttle, a reusable spacecraft that promised to make access to low Earth orbit more economical. But now that NASA has decided to restart the development of nuclear propulsion after more than 50 years, how exactly does this technology work? And why is it night and day compared to the chemical rockets we've relied on for decades? Nuclear thermal propulsion, a type of nuclear propulsion, uses atomic fission to generate thrust. The process begins with a reactor core containing uranium fuel. As uranium atoms split apart, they release an enormous amount of heat energy. This heat is used to superheat a fuel, usually liquid hydrogen, turning it into fast-moving gas that is released through a nozzle to create thrust. This method of propulsion differs significantly from traditional chemical rockets. In a chemical rocket, fuel and a chemical that helps it burn, called an oxidizer, are burned together in a chamber. The hot gases that form expand and shoot out of the rocket's nozzle, making the rocket move forward. While this process has served us well for decades, it has inherent limitations in terms of efficiency and power output. The key advantage of nuclear thermal propulsion is its use of hydrogen as a propellant. Hydrogen can reach extremely high temperatures and accelerate to much higher velocities than the gases produced by chemical rockets. This translates to a higher specific impulse, which is the measure of how efficiently a rocket uses fuel. To put this in perspective, the specific impulse of a typical chemical rocket is around 450 seconds. Nuclear thermal propulsion systems, on the other hand, are targeting an initial specific impulse of 900 seconds. This is what allows nuclear-powered rockets to achieve shorter travel times and carry larger payloads. But the advantages of nuclear propulsion don't stop at efficiency. These systems also offer significantly longer burn times compared to chemical rockets. While a chemical rocket might fire for minutes, a nuclear thermal engine could potentially operate for hours, providing continuous acceleration over extended periods. This extended burn time, combined with the higher specific impulse, opens up new possibilities for space travel. It allows for more flexible mission planning, including the ability to change course mid-flight or even abort a mission and return to Earth if necessary, options that are often not feasible with traditional propulsion methods. Another crucial advantage of nuclear thermal propulsion is its increased payload capacity. The higher efficiency means less fuel is needed for a given mission, allowing more mass to be allocated to scientific instruments, supplies, or even additional crew members. This could be very important for long-duration missions or the establishment of permanent bases on other planets. It's important to note that these nuclear propulsion systems are not designed to launch spacecraft from Earth's surface. Instead, they would be launched into space using conventional chemical rockets before being activated. This approach addresses safety concerns and takes advantage of the strengths of both propulsion technologies. But what exactly is NASA's plan? Enter the DRACO program. This initiative represents NASA's most significant investment in nuclear propulsion technology since NERVA. But this time, NASA has joined forces with the Defense Advanced Research Projects Agency, or DARPA, and aerospace giant Lockheed Martin. Lockheed Martin is responsible for the overall spacecraft architecture, which includes designing, integrating, and testing the vehicle that will carry the nuclear thermal engine. Meanwhile, BWX Technologies has been tasked with designing and building the heart of the system, a nuclear fission reactor that will power the engine. NASA will contribute up to $300 million to the DRACO partnership, giving $250 million for the design and development of the nuclear-powered engine. In addition, the United States Space Force will provide launch and launch site support to ensure DRACO has a safe and efficient path to orbit, aiming to test the nuclear-powered rocket in space by 2027 and to send cargo to Mars by 2033. Currently, a one-way trip to Mars using modern chemical rockets takes about 7 months. This means that for 7 months, astronauts are exposed to higher than normal radiation levels and cosmic rays, which will reduce muscle and bone density and increase the risk of cancer. But by harnessing the power of nuclear reactions, spacecraft could potentially reach Mars in as little as 45 days. This could allow for more frequent missions and longer stays on the Martian surface. Moreover, faster travel times could dramatically reduce mission costs. Nuclear propulsion systems require less fuel and enable more direct travel routes, possibly decreasing the overall launch mass and increasing payload capacity. The impact on mission planning and flexibility cannot be overstated. With chemical rockets, the narrow launch windows for Mars missions occur roughly every 26 months when Earth and Mars align favorably. Nuclear propulsion could potentially expand these windows, allowing for more frequent launch opportunities and greater mission flexibility. NASA's current plan is to send humans to the Red Planet by 2039, but first, they plan to return to the Moon, this time permanently. The biggest problem with staying on the Moon is making sure that the astronauts have a consistent power supply. NASA's Fission Surface Power project aims to solve this by placing a 40-kilowatt reactor on the lunar surface by the early 2030s. For context, a reactor of this size could provide enough electrical power for approximately 33 average US households. In terms of lunar exploration, this output could be the difference between short-term visits and long-term occupation. The significance of this power source becomes even more apparent when we consider the unique challenges of the lunar environment. Unlike Earth, the Moon experiences extreme temperature fluctuations and extended periods of darkness. The lunar night, lasting about 14.5 Earth days, poses a particular challenge for solar-powered systems. Therefore, alternative power generation methods are essential. The lunar South Pole, for instance, contains permanently shadowed regions that may contain trapped water ice and other valuable resources. A reliable sun-independent power source in these areas are necessary if we want water, oxygen, and fuel for future missions. NASA's plan is to develop a system capable of operating on the lunar surface for at least a decade. The entire system, including the reactor and all necessary subsystems, must weigh no more than 6,000 kilograms and utilize low-enriched uranium as fuel. This is so that it can be safely handled and launched into space. The technologies and systems developed for lunar fission power could pave the way for similar applications on Mars and beyond. While nuclear thermal propulsion promises to revolutionize our journey to Mars, some scientists and engineers are looking even further ahead. What if we could harness the power of the atom not just to reach nearby planets, but beyond our solar system? This exciting possibility is driving research into more advanced nuclear propulsion concepts. One such concept that has captured the imagination of researchers is the pulse plasma rocket, which takes nuclear propulsion to the next level by using fission reactions to generate thrust. Unlike conventional nuclear thermal engines, which use a reactor to heat a propellant, the plasma rocket directly harnesses the energy of splitting atoms to create forward momentum. According to NASA, the exceptional performance of the PPR, combining high specific impulse and high thrust, holds the potential to revolutionize space exploration. However, as with all advanced technologies, these concepts face significant challenges. Current limitations of nuclear propulsion include the need for substantial advancements in reactor and fuel technology. The temperatures involved in nuclear propulsion systems pose another significant hurdle. For instance, reactor cores in nuclear thermal propulsion systems must be capable of withstanding temperatures around 2,500 degrees Celsius. Developing materials that can reliably operate under such extreme conditions is a critical area of ongoing research. Despite these challenges, the potential rewards of advanced nuclear propulsion are driving continued investment in research. NASA and DARPA's collaboration on the DRACO program represents a significant step towards developing viable nuclear propulsion technology for long-term space missions. Nuclear propulsion is just the beginning, and the outer reaches of our solar system could soon become accessible for detailed study. But perhaps most excitingly, nuclear propulsion could lead to even more advanced technologies, paving the way for humans to explore even further into the universe.